I'm really happy to be here and tell you guys a bit about quantum machine learning. I really want this to be interactive, so please ask me questions, stop me whenever. I'm really happy to go over whatever it is that I talk about and also anything else you may want to ask me about. I'm going to start by putting up giving a sense of the landscape of quantum machine learning. There's quite a lot in this area, and I can only really cover a couple subtopics, but I just want to give you a sense that the field is much bigger than what I will talk about here. So let's talk about the QML landscape. And this is going to be very rough. It's not supposed to be meant to be anything rigorous or anything, but I think you can sort of put the landscape along one dimension. There's so-called NISQ type stuff. These are, if you haven't seen this acronym yet, it means near-term intermediate scale quantum. It's like an acronym people use to say it for the quantum computers we'll have in the next, 10 years. They'll have errors, they won't be too big, things like that. And then I'll just put universal over here. So this is like some axis that runs this way. And you can sort of imagine there will be some topics that maybe they'll work with NISQ computers, and then some that we really do need full error correction, full universal computers to run. So like, for example, there's a lot of work now on tomography plus shadows. So the idea here, and this runs the gamut everywhere from NISQ to universal. The idea here is you want to learn quantum stuff, quantum states, quantum channels, quantum processes, and you want to learn them. In general, if you try to learn any state or try to construct a state, it's an exponentially large system. But if you only care about certain things or small elements of this space, then you can probably get away with doing machine learning. And this has become really hot now. You may have heard of the word classical shadows. That's one particular technique for tomography. But we won't cover this. I just want to put it up here. Then there's quantized models. And this idea here is we have a lot of cool techniques in classical machine learning, things like linear regression, principal component analysis, stuff that is really linear algebra based. And people have taken these ideas and using, HHL or whatever it may be, have quantized them, said if we had a quantum computer, we could take these exact same operations and run them on a quantum computer. Lots of good work there. We also won't cover this, but I just wanted to point out. And a lot of these do really need universal quantum computers. It'll be tough to run something like HHL on a NISQ device. Another group is quantum kernel methods. Quantum kernel methods, if we have time later today, I will go over this a bit. The basic idea here in quantum kernel methods is that we have, with a quantum computer or any quantum device, we have quantum states, and they come with an inner product that gives some sort of distance or similarity. And with that sort of distance and similarity, you can perform learning. I know that sounds vague, but if we have time, we'll come to this and talk more about it later. The first focus of our topic, of my discussion, will be variational algorithms. And these are the most NISQ-y algorithms you can think of. The idea with variational algorithms is sort of the answer to the question, what happens when you try to make deep learning neural networks quantum? When you try to take the techniques and the structure of neural networks and probably produce the most obvious quantum model out of it. This will be the focus of our discussion, and we'll come to this shortly. I just want to put something outside of this whole framework, which is quantum inspired. And this is totally separate from the quantum world, but recently, or in the past 5 years or so, a lot of algorithms have been grouped under this idea of quantum inspired. And these are classical algorithms. They're not actually quantum. But they've been inspired, or they come from techniques to be found in quantum computing and then translated into the classical world. Oftentimes, these algorithms are used to disprove advantages in quantum mechanics, but a lot of great ideas coming there. I want to keep this separate. Obviously, we're not doing classical machine learning, but a lot of great things here too. There's probably things I missed here as well, but just want to give a sense of where we are. And again, this will be our first topic of conversation, and then time permitting will come here. Okay. So variational algorithms. Motivation. Well, ChatGPT, but more broadly, deep learning. And before I talk about what a variational algorithm is, or a quantum variational algorithm, I want to talk about how deep learning works from a very, very high level. And this is going to be very loose, but I just want you to think of this as like motivation and take these ideas and see if we can make them variational. So in deep learning, we often have some data set, pairs, say. Some n set of x and y. This could be like images and then their labels like dog, cat, whatever it may be, or it could be text and then whatever, I don't know. But you have some big data set, n can be big or small, whatever it may be, but this is basically the idea. And what you do is you form some neural network, and here I'll show it for a feed-forward network, which is just a bunch of linear layers and non-linearity. So you have some neural network. This is like a weight matrix. You have some non-linearity, and then you maybe put it to another weight matrix, W2. Again, some non-linearity, and so on and so forth. And then in the end, you get some output x. And at least in the supervised setting, you then get some output x, and you compare it to y. And you guys have probably all seen this. What's important for us is that the parameters are these weight matrices. So, W1 is some maybe big matrix, but it has entries. So, here's entry 1, 1, here's entry 1, 2, so on and so forth, entry 2, 1, so on and so forth. And these guys here are your weights. So what you do is you say, well, we have some loss function, which is over our training set. And, it could be, I'll just write example 1 here. So it could be, for example, the mean squared error loss. But there's other loss functions, and you basically say methodology is initialize these weight matrices randomly, and then iterate the following: calculate a gradient with respect to your weights, your parameters with the loss, and then update via GD, gradient descent. I hope people have seen this. If not, feel free to ask questions. I won't dwell on this too much because this is not exactly our focus, but I just want to say this is the rough framework which we're trying to quantize in variational algorithms. And as I go through this, I think it's important to think really about how this framework differs from what we're going to look at. Because just because this is motivation and this works really well, it produces everything from image recognition to ChatGPT, that doesn't mean it's going to necessarily translate directly into the quantum case. And the quantum case comes with its own problems and issues. So just keep that in the back of your mind. Another big thing I want to mention here is that in many ways, we don't know why deep learning works. These are black box models with tons of parameters. Proofs of why they work are hard to find. So, I think there's a hope that we take this and the magic sort of translates, but we should be careful when we make that assumption. Okay. Let's look at the analog. So, variational quantum analog. And in this case, we have some input state. And basically what we do is we say, let's replace this guy here with some circuit that we have parameters on, and we can vary the parameters. So what does this look like? We may have some qubits, and this goes down, and then we have, gates. So this is gate theta 1, this is maybe theta 2, theta 3. And then we repeat this. I don't know, this may be theta 4. I drew this really badly. This may be theta 5. So on and so forth. So these weight matrix entries over there take sort of the role here. When we do this procedure, we get some phi, which is now a function of our theta, our choice of parameters. So these are all gates that we can vary in some way. You can think of these for maybe an example is like a rotation. You can rotate a qubit by however much you want, or maybe a controlled knot that you control the amount of rotation in the controlled qubit. Generally, a lot of gates take the form of e to the I g t, where t is your parameter and g is some Hermitian matrix. But this is basically the setting which we're going to look at. Okay, so two examples or two instantiations of this setting. Let me give you some examples of what you can do with this. The first one is called variational quantum eigensolver. And VQE is the acronym for this. You'll see this all over the literature. The idea here is you have some Hamiltonian H. And we want to find the ground state of H. A quantum computer gives us the ability to construct a state and measure the energy. So the basic idea is, we form some parameterized circuit that outputs a state which is a candidate for the ground state. We have a loss function, which is just the energy itself. And we can do gradient descent on this. We can set the parameters, see the energy, see if changing the parameters reduces the energy, do this iteratively until we get to a minimum. And hopefully, if this works out, you get the ground state or something close to it at least. A couple comments on this. Sometimes people use the Hamiltonian itself as a gate. So you can take H to be this G here, for example. And then you have a second layer, which is not this. And then this is called the quantum alternating operator ansatz, or QAOA. I think I was told you had this in class sometime. But so that's one example of this that's well studied. But you don't necessarily need to do this. One question that comes up a lot with this is, how do you calculate gradients with respect to some Hamiltonian? And this is one of the exercises later. But for now, just know that if you can measure this energy, you can just change the parameters theta to calculate the gradients as well. Yeah?
So when you run the parameterized circuit, the final state that you get, you basically, like if this approximates and you have a final result, it will mean that the final state is the ground state of that Hamiltonian?
Yeah, so you start at some random theta, and you iteratively try to reduce this. And hopefully at the end you get the ground state. Now there's no guarantee you will get that. So well, we'll come to this, but there are challenges that come with this method. You could, for example, reach a local minima. And if you reach a local minima, it's kind of hard to leave that local minima, so it's not guaranteed. But the hope is that you have a good ansatz and you can figure this all out.
Also, the parameters that you're putting into the circuit, is the circuit, are you encoding the Hamiltonian in the circuit?
This Hamiltonian? Yes. You could. So if you have a gate like e to the I ht, you can make this one of your parameterized gates where we just parameterize with t here. And as I was saying earlier, this is one version of this is called QAOA, but you don't necessarily have to do this. But this is a very popular thing to do. So for example, you can do e to the I ht and then some like e to the I gt. So like maybe this is t1, t1, and then you repeat this for new t, g, t2, so on and so forth. And this is what is often called QAOA. Yeah.
I have a question. So if I want to read out the expectation value, like I want to measure loss on a machine, that would presumably like cut down on the kind of Hamiltonians I can consider. Presumably there would be generically like an exponential depth necessary to...
Yeah, that's a good question. So most of the Hamiltonians we care about are local. So the number of terms in this is like controlled by the locality, and you typically write it out in terms of the Pauli basis. And if it's like 3 local, then there can be at least n choose 3 terms, which is polynomial in n, and you can measure that. So there's always some sort of assumption behind this that like it's not some ridiculously complicated Hamiltonian. Okay.
Maybe another question?
Yeah.
So the T1 through Tn are the vector of theta?
Yeah, here the thetas would be like times. I wrote t here because like you're kind of applying a Hamiltonian over amount of time, but these would be parameters. This take the role of theta, yeah.
So the amount of time would be, the amount of rotation would be theta. And then for not QAOA, what would be the indication of how to choose these G's? Or, I mean, if it's not the Hamiltonian?
This is a big area of topic. It's a mix of like, we're not sure, and there's a lot of options, but also there's some, and we'll come to theirs. If you take naive systems, there's some challenges that come with it. So you have to find out a way to choose some ansatz that's targeted to the specific problem, and we'll come to this later, why that's important, and maybe I'll give you some pointers, but it's very much an open research topic. Yeah.
How do you measure the loss function?
This?
Yeah. Okay.
So, okay, let me give an example. So maybe your Hamiltonian, so your Hamiltonian will be a sum of like local terms. And each of these local terms you can say is a Pauli. So like, I don't know, maybe h1 is equal to x, I, or something like this. And if you want to measure this, well, there's many ways of doing it, but one way is you just look in the basis of x. So you apply, I think, a Hadamard transform, and then you perform a computational basis measurement. And then you get an eigenvalue out of this. I'll give an example later, and I think hopefully it'll become clear.
So you need some sort of tomography, like some sort of
Sampling, yeah, you have, all throughout this, like when you have a state and you want to perform this measurement, you're going to always have to do sampling. So, and this is a good point, like you can't make this too deep for that reason, because if you ever want to measure anything in quantum computing, you're going to get a probabilistic outcome. And you have to measure it many, many times for that to be good. Okay, all great questions.
Just a quick question. Are there analogs of sort of the layers of deep neural networks in the quantum thing? I mean, obviously this is all in the circuits that you're building to do this, but it seems like it can translate that cleanly.
It doesn't, no. It doesn't translate that quickly. I think the hope translates that like we have these really big networks that really work, and hopefully this does the same. And Maybe it doesn't. We'll see. But yeah, it's a loose analogy, and that's why I kind of said we should keep this motivation in mind. Yeah. Okay. Another example is what's called unitary compiling, and this is more. So this is really just an optimization problem. There's no learning. There's no data set. But here you actually do have a data set. So for example, we may have some pairs of phi in k, phi out k. So, we have pairs of input and output states that we say want to find a circuit that recreates this. And we want to find some u theta, so our circuit there is our u theta, and we want to find some u theta so that, for all states I wrote phi, so that psi out k is equal to u theta psi in k. So we want to find a unitary, or I should put this approximately true. We want to find some unitary that roughly constructs the state we actually desire. And our loss function, will be like some sum of some distance metric of u psi in k psi out. Okay. So some distance metric, inner product, fidelity, whatever you may pick. And what's the reason? Why would we want to do this? Well, in the NISQ era, we don't have universal computers, but we may want to maybe compress a circuit so that we can actually run it on the quantum computer we have. That's an example application. So, if you want to run HHL, you don't have, 100 layers, but maybe you can do it in 20 layers approximately. So you try to learn it. Yeah.
So here your goal is to find theta such that, on average, you want to do this across the whole data set. It's a single theta for the whole data set, not a different theta for each data point.
Yeah, here you want to find the right parameters theta so that for every k, you get this mapping approximately. Yeah. Okay. Now this has all been rather abstract, so I'm going to give a simple 2-qubit example and we'll run through it so that maybe it makes more sense. Okay, so let's look at a VQE example. And in VQE, you want to find a Hamiltonian. You want to find the ground state of a Hamiltonian. So I have to give you the Hamiltonian we're going to try to find the ground state of. So our Hamiltonian will equal y minus x minus z. Does anyone know what the ground state of this is? Or want to venture a guess? Let me write the matrix out and then maybe people can take another guess. -1, 0, 0, -2. So our h is this. 0, 1, 0, 0. Anybody want to venture a guess at the ground state? No guesses? Okay. What's that? I can't hear. Bell state, which one? Yeah. Yeah. So I heard it. What'd you say? Yeah, maybe I'll write. I think we're saying the same thing. It's the state. So this is like the cat state. Sometimes people call it GHZ state. It's one of the Bell states. Yeah, it's just a completely entangled state. If you measure 0 in one qubit, you get a 0 in the other one, you get a 1. And if you plug this in, you'll see it's an eigenstate, and it has the lowest energy. But let's see if we can actually recover this using VQE. This is obviously a small matrix, and we can do this all exactly, but in reality, this matrix is like 2 to the n by 2 to the n, so I would never be able to write this whole thing out, but this is just a toy model. So another thing I have to give you when we say we're going to do this is the ansatz, the circuit. So here's the circuit we're going to use. We start at 0, 0. We have one gate, which I'll tell you is parameterized by theta. And I'll tell you the form of this. And then we have a second gate, which is a controlled rotation. And I'll give this parameter the name alpha. And then this produces our phi, which is a function of theta and alpha. So these two circuits, this gate here, our theta gate, does just a 2D rotation. So it's cosine theta negative sine theta, sine theta, cos theta. And this one is the same thing, but it's controlled on the first qubit. So let me just write it out, just so we're all on the same page. This guy is a 4 by 4 now, which does 1, 0, 0, 1. And then here we have 0, 0, 0, 0. And then we plug this guy in, but now it's a function of alpha. Cos alpha. So what does this gate say? It says if the first qubit is in 1, then we apply rotation by the amount alpha. And if the first qubit is 0, do nothing. OK, so let's say we randomly initialize theta and alpha from 0 to 2 pi. Who thinks this will work? If we do gradient descent on this from random initialization, who thinks this will work? I'll give you a second to think about it. Who thinks this won't work? OK, a few hands go up.
With gradient descent, it should work, right? Because that could approximate the Hadamard and the C naught, if we could do that.
Yeah, so let's ask, what are the right parameters that we want? Let's first ask, first question you should see is, can this actually get our ground state? So can we get the ground state with parameters alpha and theta? What are they?
Like the first has to be like 5 by 4. And
Yep.
the second has to be, I think, 5.
And the second has to be
5.
pi or pi over 2?
Because it's cosine.
Pi over 2.
Yeah. OK, so these are the right parameters. So in a sense, our ansatz is good. Now the only question is, will gradient descent recover these parameters? And it seems like there was skepticism in the audience, but let's just draw it out. So we can draw out the landscape. So here is theta, and here's alpha. And I'll put a contour plot here of the loss. So like you can kind of see what the energy is as we change the parameters. And our target is this guy here, so pi over 4 and pi over 2. So I'll put a big star here. That's what we want to get. And actually, I ran this on my computer. It looks something like this. So as I draw these, this is like the smaller and smaller energy. And there's something here, similar here, I think. I forget the exact thing, but basically the point is, if I start randomly, let's say at this point, then I do gradient descent, I'll maybe go that direction, and then I go this direction, and then we eventually get there.
What is like the phase on this? Like I'm just wondering if like the attractor might be too small.
This attractor?
Like the basin, yeah.
Oh, this is like, I think that goes from 0 to pi and 0 to pi. So like it'll work, yeah. You can run this on your computer, just run this model, you'll see it. It should work. And I kind of picked this so that it does work, to give you some hope that this will work. But later we'll come to the problems of this whole methodology and where the active research is. Yeah.
How did you decide that the circuit should be that circuit specifically?
I picked it because it gives you the right answer. In general, you don't know that, and that's where the ideas come in. So QAOA is one reason. One of the so QAOA is one common circuit because it has some like clear connection to the Hamiltonian you're trying to learn. This goes back to adiabatic algorithms, for example. If you slowly shift the Hamiltonian, it stays in its ground state, and QAOA is like one way to realize an adiabatic algorithm. So there's some motivations like that. But here I just picked it because I know this is the right answer. And that's an active area of research. What is the right circuit? Because we don't know the right answer.
But also you took the sort of more generic, maybe if you had another single qubit rotation on the bottom qubit, that would already be like the most generic quantum circuit you can choose, so maybe that's already. Yeah,
two qubits, it's 4x4, there's not much freedom, yeah.
I guess if we had n qubits, you could still write it as single qubit rotations on all the qubits, and some sort of 2 qubit entanglement gates on all the pairs, and that would cover.
Yeah, so 1 and 2 qubit gates are universal but you need exponentially many layers potentially, and we can't do that. Yeah, but there is like, if your Hamiltonian is simple, you probably shouldn't need all that many layers. That's the whole hope behind this area. Okay, so I think for the next 10 minutes, I'm going to step back from this problem and sort of just enter learning theory, which is the study of what we can learn and how we can learn it. And our goal is to kind of see two things, like how does this differ from the classical setting of deep learning? And two, what type of problems and challenges arise when we try to do this? And to do this, we kind of need to jump into a bit of background into learning theory. Because I want to get a little technical. Yeah?
Before we move on from the question, so you have the state,
Yeah.
you have the Hamiltonian matrix. So you told us that that's the ground state, and you just showed that circuit can give us the state. But how do you measure the energy?
The energy here?
Yes.
Okay, so for example, if you want to measure, you measure each of these terms individually. This is one way to do it. I'm not saying it's the only way, but you can measure each of these terms individually. Let's say we want to measure ZZ. All we do is we take this state and we measure it, and we get a bit string, and then we take the product of the bit string because the parity is equal to the eigenvalue.
Do you just calculate the matrix multiplication and find the Hamiltonian, or is there some other way, like in the quantum circuit, that you measure the energy using?
Yeah, so like each of these terms you can measure individually and then add it. So you just rotate into the basis of the poly and then measure in that poly basis. That's one way. There's other ways too. Yeah. Okay.
Is the loss function
Classical. Well, you measure the loss function quantumly, but the rest is classical. Yeah. So sometimes for that reason, people call these hybrid algorithms. They have a quantum and a classical component. Yeah.
Sorry, this question might be coming from more of a physics background, but like these Hamiltonians are assumed to be like constant across time. So is there any algorithms that deal with like time varying Hamiltonians?
There are problems with VQE is usually you're given a Hamiltonian but there are stuff like that, yeah. I come from a CS side, so I'm not really 100% sure, but okay. Well, let's do some learning theory. And I'm going to only go over the very basics, but it should suffice for our purpose. So, let's say we have some distribution D, which is over pairs of data. So, I don't know, again, this may be images of dogs and cats and their labels. And there's some distribution D, which gives you these pairs. We don't have access to this distribution, but you can think in the world maybe it exists, and there's some math we can do with it. As I mentioned, we're given finite data set. xi, yi, where I is going from 1 to n. So in general, we're given n data set, n elements of this distribution, and we can assume they're IID, independent, identically distributed from this distribution data, from this distribution D. And usually our loss function takes the form of something y hat y. So we have a loss function which looks at some prediction y hat. So y hat, you know, if we have f of xi, so we can plug in, for example, xi, yi, and then we sum this over our whole data set, and this is our like sort of empirical loss. Sorry, this is maybe, I can, you know, sometimes people give this the hat notation. So our empirical loss is some function f, and maybe I'll put a parameter theta here to say that our f is like our neural network or our variational algorithm, something that has parameters theta, and we can then compare with our targets. So what we really care about isn't this loss, but the loss over our distribution D of L f of x, y. And maybe I'll write this a little cleaner so that you kind of see what I'm saying. We have some distribution x, y, which is distributed according to D. So we get pairs according to this distribution. We take the expectation over the whole distribution, and we want to measure this loss. This is our true error, sometimes called test error. And this is what we really care about. We don't just want to minimize our data set. We want to minimize the function itself. But this is a problem. We don't have access to D. Yeah. Good question. That's what I'm coming to. Great question. We don't have access to D. We do have access to this. So if you kind of look at this for a second, this is sort of like L. This L is like a random variable, and this is like an estimate of it from n samples. So maybe we can argue there's like a statistical convergence. So what we do is, you know, a common step in learning theory is we say, we have this guy, and then fx, y. And then we add and subtract something, the same thing, which is our empirical loss. So we say, let's just add and subtract this. I should put a 1 over n here. So let's subtract our empirical loss. And again, the same thing. So this is valid. This is OK, because I can just, oh, sorry, I want to do minus up here and plus up here. Sorry. And this is OK, because we're just adding and subtracting the same quantity. And, well, this guy here, this quantity up here, this is a statistical quantity. It's saying how much does the expectation of some random variable deviate from its empirical estimate of n quantities. So it's often called the statistical error. But I'll call it generalization gap. Because, well, this is sometimes called the generalization error, and then this is the gap of the generalization error from your empirical error. And if we stare at this for a second, this is like an optimization. This is saying I have some quantity which I can optimize, and I want to minimize it. So it's kind of the same exact thing you see here. So this is the empirical error, sometimes called the optimization error. And the question is, we can minimize this, or at least we have methods to do it, but we don't really know what's going on here. So is there a way we can bound this error so that all we care about is this one? And this will be a homework problem. But in general, in many cases. I should say this is not true all the time, but if you have some function that has p parameters, so p params, so there's p parameters in your function class. If p is greater than, we'll say much greater than n, then generalization gap is well bounded. So in your homework, or in the exercises, I should say, you'll see a situation where gap is equal to order square root p over n. And again, this will be in the exercises, but the basic intuition is that every time I add a parameter, I'm sort of doubling the search space, so it increases exponentially with the number of parameters, the search space. But at the same time, as I add elements of my training set, then the empirical error, or the empirical estimate, will exponentially converge to the true estimate. And these two things sort of counteract and...
This would be big though, right? If p is very greater than that?
Yeah. Oh, sorry. Sorry, had this, you're right, yes. Sorry, good catch. Good catch. Yes, of course, as you add more data, this should be easier to do. Good catch, thank you.
But I mean, I've had friends explain this to me, which has also puzzled me, is the fact that like quite often you are in a very, very like over-parameterized regime, and somehow still it seems to generalize well.
Yeah.
Like you have like 100 times more parameters than you have input points, which...
Yeah, exactly. This is when people say...
opposite of that.
Yeah, so when people say we don't know why deep learning works, we're actually in the regime where p is greater than n, and all this stuff is thrown away. And that's one of the reasons why people say machine learning, we don't know why it works, because we can't really bound the generalization error, and we have these complex models that sort of should go against this sort of baseline theory. So, well, let me give some perspective. So some perspective and kind of exactly what the person's question was. Let's look at classical versus quantum. And when I say classical, I mean like our modern deep learning regime. So let's really question this assumption that these things are the same. And like number of parameters. So like ResNets, you know, our image models are somewhere, I don't know, about 10 million to 100 million plus. They can have more even. GPT-3, which is, you know, our all favorite ChatGPT. Does anybody know how many parameters ChatGPT has? Want to guess? Yeah, 175 billion. Which if you think about it, it's like a function of 175 billion numbers. That's kind of crazy that it works, right? I don't know. Anyway, a number of data. You know, just some example data sets, 50K CFAR. This is a common image data set used. 10 million ImageNet. Yeah, or N here, yeah. Text, it's hard to say, but like terabytes of text. There's not really an exact analog to images for text, but there's terabytes of it. But if you kind of look at this, like, at least for images, it's like pretty clear this is an order of magnitude smaller than the models we use it to train on, and it still works. So this all goes out the window. I shouldn't say it goes out the window. We need to work a lot harder to prove stuff like this. And it isn't active area research, but if you actually look at generalization bounds machine learning, they're pretty vacuous. They don't really work well. So if you want to work on a problem, that could be something. But anyway.
Is there any proof for a relevant model with like in the over parameterizers?
It's hard to find. There are some that are getting there. If you make some assumptions, then you get nice proofs. Like if you have infinite width layers, then there's like some nice theory that comes out that it comes. Anyway, there's some stuff, but in general, no. Yeah. And then one thing I want to say is like runtime to calculate gradient to error epsilon. And this is, I should just say, this is about like polylog. So polylogarithmic and the error you want. This may look weird if you see this for the first time, but I just want to say like, all this means is like if you add a bit to your numbers, you like increase the precision of a number, the runtime you need only really goes up linearly with the number of bits. Because, well, if you want to like if you want to like be doubly precise, you have to add a bit, and then decrease this by half is like a unit increase in the log. So we'll see this contrast with the quantum side, but I just want to say this is what computer precision is, that you can add bits and get exponentially more precision. What about quantum? Now we don't have exact numbers here because we don't have quantum computers, but if we had like 100 qubits and I don't know 20 layers, this is about like 10K at most. We don't really have data sets yet, or we don't have ideas yet, but again, it's going to be probably the same. I'm just going to say roughly the same as this. I don't know, large enough, I'll say. Like, it's believable that we can get 10,000 data points when we want to run a machine learning model. If not, we can reduce this number, but it's going to be like something feasible, right? It's not going to be 175 billion. I just want you to think of this loosely, just to see the big, vast differences here. And then finally, I want to point out here that this is order 1 over epsilon squared. It's not polylog. It's not logarithmic. And this is because whenever we calculate something in a quantum computer, we have to sample. We get a distribution on the output, and we have to sample that distribution to get the true value, and the error, the number of samples we need, grows as this. And this is much worse than this. This will be another exercise, actually, to see this, but this is kind of a roadblock. It's saying, like, if we want to increase, if we want to double, if we want to like increase the precision we want, or like if we're getting close enough, we have to do even more, far more calculations. So we have to be really, really careful about how we design these. Yeah.
I have a question. Is there any like efficient ways to load in data into a quantum computer?
Yeah. If it's classical data, it can be tough. But there are ways. There's quite a bit of work there. I will say if it's classical data, there's like, it can be in general challenging to do, like challenging in the sense that it could be computationally inefficient. But a lot of times, like you have quantum data that you don't need to really care about the classical loading. Or in VQE, for example, we don't really have data. So yeah, but it's a good point. In general, if you want to like load 175 billion data in here, it's not going to work. Yeah. And maybe in the future we'll have QRAM and stuff where this becomes doable, but that's not really the focus of our topic. Okay, so I guess the message here is that it's really easy to scale these. We can bump these numbers up quite a lot, but it's harder to scale this. So if we're going to find some advantage here, we kind of have to be careful. And this is one of the first sort of points where we see a challenge with quantum models. Okay. All right. Okay, so let's say we find a situation where we find some hopes, but I kind of haven't really talked about the ansatz. So we have to pick some ansatz or some circuit that we can vary and see if this will work. And the main challenge, I should say the central challenge in a lot of this, is that circuits are initially random. And if circuits are big enough, then this randomness is close to so random enough that it fills the whole 2 to the n space. Yeah? I'm coming to that, yeah. So you typically start with some gate, some initialization, some circuit that you have a bunch of parameters in. Just hold off and I'll come to your question, yeah. And the worry is that if it's even little deep, it becomes pretty close to the uniform randomness over all unitaries. And this is a space that's of size 2 to the n. And like for VQE, we only care about one dimension of this space. We only want the ground state. So if it's so random that it's filling this 2 to the n space, and we want to find one thing in this space, we kind of have a problem. I'll be a bit more precise, and this will be a focus for the next, 10, 15 minutes. But that's the intuition that in quantum, one thing that's really different is that our space grows exponentially with the number of qubits. Not true classically, and we have to be very careful to avoid this issue. Let me just put some math up here. I'm going to, for the next couple minutes, put some math up here to define what I mean by close to random. And then we'll use this to show some results of why it's really hard to train these things. So we have a concept called the K-design. Which means if we have some, let's say we have some distribution mu over unitaries, and mu matches har up to kth order. Well, what does this mean? It means that if I took my unitaries from this mu, then u star, so this is not dagger, but u star, u conjugate, but you just take the conjugate of every entry. Tensor k is equal to the same if these were har random. Oh, and if you haven't heard of har random before, it just means uniform over all possible unitaries. Some intuition behind this. This is saying that, like, these are sort of the moments, I guess you can think of it that way, of the unitary distribution. And it's saying we have some distribution mu that's not totally uniformly distributed, but at least it agrees up to the first k moments. And the moments look like this. We're actually only going to care about 1 and 2 designs. So let me give some intuition behind those. So 1 design, e.g. polys. So, you know, all the x, y, z, I, tensor n. So all the n qubit polys generate a 1 design. And another way of writing this is E. So if I have any matrix U, and this is kind of like twirling it, so it's saying take the average of the matrix where I randomly rotate the left and right by some unitary. This is often called the twirling operation. This always equals trace m over 2 to the n times the identity matrix. And this kind of makes sense because, like, imagine M as a state, it's a density matrix. If we rotate it by unitaries, we don't really know what state it is anymore. It can be anything. So it's kind of saying it becomes the completely mixed state. So that's one intuition for it. And polys are an example of such a 1 design. But if you kind of think about it, polys are all product unitaries. They don't generate entanglement. They are kind of useless. So we probably need something a little stronger than this. So it comes to a 2 design. And this will be the ugliest formula I show today. And I apologize beforehand, but we'll use it in a proof that I'll probably get to after our break. But let me just write down the formula, and then I'll explain it. So Same thing here, a distribution mu is a 2 design. If we have the same thing, but now I do a tensor product, so M now is a bigger matrix, and then we have, and this guy, and this is going to be ugly. Let me just write it, and then I'll explain it. Oh boy. Okay. And then another factor. I'm already making a mistake. Okay. Okay, so, and this W is the swap. Okay, deep breath. Let me explain this formula. So I wrote out a big long formula. So this is saying if we have a 2 design, then it looks something like some constant that's exponentially small times I plus W, the trace of that with respect to M, where W is the swap matrix. So it takes BA and swaps it with AB. It sort of flips the 2 things. So like if you have a state that's a product state, it'll flip the 2 around in the circuit. And you have these 2 components here. What generates this? What's an example? The Clifford circuits. I don't know if you guys have seen this before, but Clifford is an example. And these are all the states that can be generated by C naught, Hadamard, and S. And the S gate is equal to something that kind of looks like the Z, but it's just an I here. So all the circuits that you can generate from these 3 form a 2 design. Actually, I think they form a 3 design, but if it's a 3 design, it's also a 2 design.
In the first line, U out of product U, is that really just X out of product X, Y out of product Y, or you're including X out of product Y, X out of product Z, and so on?
Here? Yeah, this is,
Like, what about the dagger? There's like only one dagger in that.
Sorry, say that again?
Like, what about the stars? Like, they don't seem to line up.
You're missing a dagger on the final U.
Sorry. Yeah, so this is like a 2 to the n times 2 to the n by 2 to the n times 2 to the n matrix. Okay, this is kind of a lot of math, and we'll use this, I promise. But I just want to give a sense of what we mean by close to random. This is not, yeah, go ahead.
So M is a matrix. Are there any conditions on what M is?
No, that's the whole point.
So oftentimes I've seen 2 designs written down in terms of like matching up to observables.
Mm-hmm.
So there, would M be? Would you only care about like M when M is like Hermitian, or are these definitions equivalent?
Yeah, we're going to only care about M when it's Hermitian. Yeah. Yeah.
What do you mean by K design? I don't understand. Like, what's K design and what's EU?
So mu is like a distribution over unitaries. So like our circuit, we have some circuit, and then if we initialize the parameters randomly, we get some random unitary out. And that'll be our mu. And I want you to see mu, you're going to think like it's some distribution over our initial circuit. But this circuit won't be completely random. It won't be uniform random. It'll be something close to uniform random. And this is a way of saying how close to random it is. So like if you forget unitaries and think like just random distributions, this is like it's saying it's agreeing with some distribution up to the second moment. Okay.
So one question.
Yeah.
So you mentioned before talking about K designs that you don't want things to be too random. Is that right?
Yes.
So you want these things to be K designs, but not with a large K, something like that.
What I'm going to show is that even if it's a 2 design, you're in trouble, which is a super strict issue. So what you really need is to avoid, you only want to search the space which you really care about. If it gets anywhere close to a 2 design, you're in trouble. Okay, let me just say the formal statement and then we'll take a break and I'll prove it after we come back. But this randomness problem shows up in many ways, but the first way it showed up is what's called barren plateaus, which I'll describe now. But I don't want you to leave this thinking that this is the only issue. But this is the first one people discovered and have really analyzed. So what's a barren plateau? Barren plateau is basically saying that what we care about in observation are gradients. And at initialization, if we have a 2 design, then these gradients are exponentially small. So the formal statement is the following. Let's say we're given some E theta. So we have some thetas, and it gives us some energy, which we can say is equal to 0 U theta dagger H U theta dagger 0. And then we say where, U theta is just equal to some I equals 1 to L, I don't know, e to the I, G, I, theta I. So it's like some circuit that's just a bunch of controlled rotations, and we have L layers of it. But we say that U to the theta is a 2 design, meaning if I randomly initialize the parameters theta, I get some distribution over unitaries, and it forms a 2 design in the sense that I described over there. Then the variance of DE over d theta L, is equal to 2 to the negative omega n. This just means that it grows at least exponentially. It decays at least exponentially in n, this omega n notation. It's saying that there's some constant that bounds it from below. So this says that the gradient of the parameter decays exponentially in n. And I wrote this as dE over dL, the last parameter L, but it holds true for other ones. I just picked this so that we can go through the proof today. And it keeps it easy. But I promise you that this statement holds true. A similar statement holds true for every parameter. So if you look at this, it's saying that as you add more qubits, the gradient decays exponentially fast, if it forms a 2 design. And this is a problem. And later on, we'll come to look at how you can address this and fix it. But I guess we'll take a break now, and then we'll come back and prove this. Thank you guys for talking to me between these at the break. I realized that this probably didn't make sense to a lot of people, so I'm going to run over it again. And I'll try to give some overview of it. So let's just be specific to the setting we care about. We have some circuit, it takes some form like this. I don't know. I'm just going to draw a bunch of gates. I don't know. And then this goes on for a while. This circuit we initialize at random when we start. So these are all gates that have parameters. And at start, we initialize them randomly. And you can say that this circuit forms a unitary, which is a function of theta, our parameters. And if theta is initialized randomly, then u theta will also have some distribution over unitaries. And that is what we call mu. So we sort of push forward the distribution of theta into mu, which is a distribution over unitaries. It's not going to be uniformly random over unitaries. So there's a concept of uniform randomness over all possible unitaries. These are all the 2 to the n by 2 to the n unitary matrices. It won't be uniformly random because you need exponentially many gates to do this. But we ask instead, how close to uniformly random is it? And this brings up the concept of 1 designs and 2 designs. A one design is any mu, distribution mu, which if we were to replace this distribution mu with the true Haar random, the true uniform distribution, this formula would hold. It's basically saying, take M to be a density matrix. It's saying whatever density matrix you give me, I replace it with something uniformly at random. And I can do that by just like flipping every qubit. If I flip every qubit at random, I have no idea what the state is, right? So it's uniformly distributed. So one layer, we get a one design. But if you kind of think about it, like flipping every bit doesn't create any correlations between things. So we need something a little stronger than that. We want to make an argument about variance. And a variance is a second moment. This is like a first moment. So if we want to make an argument about second moments, we got to go to two designs. And we're trying to make an argument about variance. We need to go to the two design, which is sort of the second moment. And there's this ugly formula. I'll come to that one second. There's this ugly formula, but don't look at the details per se. It's kind of a plug and chug, but it's kind of what it's saying. I hope that helps. Yeah, there was a question back there. Yeah, so forget quantum states. Let's say we have some bit string. And we want to replace this bit string with something that's completely random. One way to do that is just flip every bit with probability 0.5. Same thing here. It's saying like if you were to take every qubit and apply a random poly, which is kind of like applying a random bit flip, you'll get a completely mixed state.
What is M? That's the input, or?
It's any matrix.
Any matrix.
If this holds true for any matrix. So density matrix is a matrix, and
but it's fixed over the expectation value.
yes, yes.
Can you call shadow tomography something like one design?
Yeah, I guess there's like some ties there. Yeah, it's saying like you want to find some compression of the things that it recovers. Yeah, maybe. I don't know. There's probably Okay. I apologize if this doesn't make sense, but we really should move on. But please stop me again if this is starting to make no sense. But I think as I go through this, you'll kind of see why this arises, this proof. And you'll kind of see why we need this over here, and maybe that'll help this whole thing make more sense. So let me just call this quantity here, I'll just shorten the notation. I'm just going to say D. Like I don't want to keep writing fractions. So variance of VEL. What's the formula for variance? It's equal to the so it's equal to the average. This quantity here is like an average. I don't want to keep writing expectations. So the average of the square of the quantity minus the square of the average, right? So let's calculate each of these two quantities, and we're going to calculate them using the formulas over there. But first, before we calculate it, we should write out what our gradient is, and we have the form of our circuit here. So let's calculate this, and if you were to calculate this guy, you would find, well, let me write it out a bit. It's equal to this. Let me plug this guy in, but I'll plug it in this way, e to the I theta 1 V1, e to I theta L VL. I realized I changed notations here. Let me be consistent. So just the gates are now V's. I have this in my notes here. I apologize for changing it on you, but I'm just going to be here so I don't confuse people. So we want to calculate the gradient with respect to this kind of long formula, but we want the parameter here, this theta L, the last layer. And if you were to do this, you would find it's equal to I times U VL H U 0. So u here is just u theta. I'm not going to put parentheses and all just to make things shorter. And you take, this is just the commutant, so VL, the commutator, sorry, minus HVL. And that's the formula for the gradient. So let's calculate now these two quantities, the expectation and the expectation of the square. Okay. CLE is equal to EU. And since it forms a 2 design, we can just assume it's Haar random because its first moment agrees. So, notice here we have this twirling, by the way, which is what the form is over there. You kind of see why I showed that earlier. This is a twirl here, and you kind of see it over there too. Right? I'll run here and just show you guys. Notice how similar this is to that. Yeah. Okay. EU. And we plug this guy in, 0, U dagger, VL, H, U, 0. And you can pull this expectation in because it's linear. So we have expectation U with respect to this inside, and we then use our formula there. So this becomes trace of VLH over 2 to the n. And then we have I0, identity, 0. This is just plugging in the formula I have for one design. And notice that this trace is 0 because of just this. So this guy is just equal to 0. And this kind of makes sense. The average value of your gradient, if you have something random, is just going to be 0. You don't know if increasing it or decreasing it really reduces the loss function. So this guy goes away, and all we have to care about now is this quantity. Okay. So let's look at the second quantity. Okay, so this is a bit more work, but let's write it in. And I'm going to skip a lot of steps here because a lot of it's going to be algebra. But let me just write out the steps, and then we'll plug in the formula, and then from there we'll skip a bunch of stuff because it's algebra, but hopefully you can do it at home or something. Okay, so again, we have a 2 design, so we can replace whatever distribution we have here with the truly Haar random, truly uniform at random, because the formulas will agree. And we have I times 0, U dagger, VL, H, U squared, and I have a squared here. So, and I kind of want to massage it into a form that looks something like this. How do we do this? Well, we have a negative I squared becomes negative, so let's just put a negative here. And then what I'm going to do is, well, let me write it out. 0, 0, U, VL, let me just put parentheses around this, H, what do? I just did all this and then tensored it twice everywhere. Because like everything here is tensored, so it just becomes the product, right? So it just becomes squared, same thing. And notice here again, we have the right form we need to plug it into this. And this is why I said 2 designs kind of are variants. You know, like you need a second moment to get variance, and this is where it sort of comes in. Hopefully this is all starting to come together. Okay, so we bring the expectation in, and then this whole business becomes a rather ugly formula once we plug that in. Okay, well, let me just write it.
One of the terms will probably go away because you have a swap.
Yeah, I'm going to skip a lot of these steps because you should do it at home, and if I would be doing it, it'd be like another couple blackboards. But it's just algebra. Once you have this formula stuff, you just have to run through the algebra. So I'm just plugging in this guy here. Oh, no, not a fraction. Combinatorics. Sorry, my handwriting is quite ugly, but I hope you get the idea. And I can't promise I didn't make a mistake, but you get this, and well, if you run through this, which I'll let you do at home, you will come to the conclusion that this quantity is exponentially small. Let me just erase this. If you were to do this whole thing, you would find that this quantity is basically, or actually it's not. If my math is right, it's actually equal to okay, so let's just do an approximation here. This guy is basically 1. It's 1 minus 1 over 2 to the n. It's basically 1. And this is basically 2 to 2n. And then this guy here looks funny, but like if VL and H both have eigenvalues that are equal to 1, its square is going to be roughly equal to 2 to the n. So this is about 2 to the n over 2 to the 2n, and again, roughly equal to 2 to the negative n. And this is kind of what we're trying to say, that our variance is at least decaying exponentially. Say again?
In the over the parenthesis has to be it. First one. The first parenthesis, has a
Oh, yeah, sorry, yes. I can't promise I didn't make mistakes. Yeah.
So morally speaking, to go from the middle left chalkboard to the right chalkboard, can you just not escape these inverse factorial, or these like the inverse factorials that you get?
Yeah, this guy is what kills you, yeah. Yeah.
Can you explain again how you got the numerator to be 2 raised to n? Roughly?
This numerator? So VL and H are both like, think of them like polys, roughly. They have order 1 eigenvalues. If you multiply two operators that have order 1 eigenvalues, they're going to have order 1. They're going to have constant eigenvalues, and there's 2 to the n eigenvalues. So the trace is roughly 2 to the n times a constant. Again, very, very rough. There's constants here I'm ignoring and stuff, but the whole point is that it decays exponentially. Yeah.
I have more questions. Who is the original Baron-Plateau's result attributed to? Do you know?
So Jared McLean's and Google's work. I can send you the paper if you want. Just ask me after. But this has been studied way beyond that work. It's I think it's the easiest to analyze. It's not the only problem, but it's the easiest to analyze, and it's why a lot of work has come here. Okay.
We care more about the fact that the gradient went to 0 rather than the fact that the variance is exponentially decaying, because that's what's going to kill us in the gradient descent.
So the average is always going to be 0. Like, no matter what you have, like the average is always, you don't really know what direction to go, right? That's kind of what it's saying. The whole point is that, like, if the variance is also 0, then like the magnitude of the direction is also really tiny. It's like you know what I'm saying.
This, you said that is a 2 design. Is that obvious or?
That's what I'm coming to, yeah. So I've made a statement that this is a 2 design. So now the question is, when do 2 designs arise? And I'm actually going to just step back and just ask, when do barren plateaus arise? So basically, recent work, my favorite is 2.2. I'm just going to put archive numbers from now on, just so I don't have to write out a bunch of titles. So 2.2 3.0614. If you have some gates, so like this is a k local gate, so you at most allow interactions between k qubits. So this is k, this size, this size is k, and then you have some gate that goes on and so forth, and it's d layers. So if you have a d-layer deep circuit with k local gates, this paper shows that there's exponential decay in d and k. So both d and k, I'm putting aside some details here. Basically, if d and k, these gates are close to random within the k local system, then you're going to get exponential decay in both d and k. So after n layers, you're essentially totally random. So it's saying you have to be like kind of logarithmic in the depth for this to work, or constant depth. Even something like linear, you're already in trouble. This problem has been addressed by changing the ansatz not to be random like this, and other various tricks, doing measurements and fixing initialization, but it's not the only problem that arises, because as I said earlier, like randomness is not just at initialization, but everywhere throughout the problem here. So my point is that there's been a lot of papers to address the barren plateau, but there's still other issues. And I'm going to just give you a survey of the works now. You can ask me more later, but I'll just put some papers here that you can look at and see the other issues. So the first is that there's bad local minima. If you take like a random unstructured ansatz, like something that has nothing to do with the problem, you just try some random ansatz and then try this, it has bad local minima. Essentially, the loss function looks something like this. It has, maybe some like dips here, but it looks really flat and there's a bunch of traps. Like if you were to do gradient descent here, you maybe get stuck here, you maybe get stuck here. There's a ton of traps, exponentially many.
Can't you address this by varying your learning rate? You can't just change the learning rate.
The whole point is that like if there are too many traps in any gradient algorithm, no matter what learning rate really, you're always going to get stuck in a local minima.
If there are too many, I'm just saying if there's a few, you can't make it.
Exponentially many, yeah, in general. Yeah, same issues here. And this is work that is, I'll just put a couple papers. One of these is mine, actually, so don't read that one. Another issue is that gate errors. So quantum computers have gate errors, and this also leads to the same issue.
110.
Sorry?
The left archive number is 2110.0.
2479. And then
what are the first 4 digits?
2110. 0.02479. 2205.05786. So this paper, one of the papers you can look at here is 2007.14384. And you can bug me after if you want to hear more about these. And then a final issue, which I also think is really important, is that oftentimes we ignore that there's like classical algorithms which also can do this stuff. And a few papers actually that precisely look at this. 2210.13200, 2211.16998, and 2008.02199. So a lot of times people say, look, we figured it out. There's a problem here that we can solve, but then someone else says, there's already a classical algorithm. And this has happened quite a few times. Okay, so I spent a lot of time saying negative stuff about this whole system, but I think we started out hopeful, and now we've probably went the exact opposite direction, which is kind of the goal. But I want to say there's a lot of areas for hope and promise. I don't want to say it's all doom and gloom, because it's not. So promising. And this is probably a bit of my opinion and also people's work that I just want to highlight. Structured ansatzes. Like QAOA, for example. So a lot of these proofs fall apart when you have something like QAOA because it's not random, it's tied to the problem. A couple papers here, 1411.4028 and 1910.08980. And another thing, which probably the physicists here are well aware of, is that there's a lot of symmetries that you can take care of. And symmetries take your 2 to the n dimensional Hilbert space and confine it to a much smaller space. And if you can confine the space with those symmetries, then your randomness might be fine. And this is hot both classically, symmetries come in convolutional neural networks in a ton of different places, and now in quantum too. So if you ask the people who are running these algorithms, I believe they would say this is the biggest area of promise. So yeah. Okay, I have till 4:30, right? Or
yes, you can go.
Okay.
Nominally, yes.
Okay.
Seems to me that archive has turned literature search into like an alcohol test or something.
Yeah.
So many numbers.
Yeah, there's been so many papers in this field. I think part of it is because of the hype of classical machine learning has come into this. And there's a lot of good work, but there's also a lot of things to work on. And I don't want to overwhelm you here. I really don't. If you are interested in this, you can come ask me later. They're all kind of different problems in nature. So
can we comment a little bit about this, this decomposition into K local gates and T layers? Because, often in quantum algorithms, you really want to create this, distributed entanglement, large cluster states, and so on. And this sort of says, don't do that because, this application, you're dead. Or is that not quite true? Is it more of a decomposition problem of your?
I think the statement I want you to go away with is people often assume adding power to an algorithm helps in learning. But also when you're doing machine learning, you also have a search problem. So if you make your system more powerful, you also have to find the thing in a larger space. And this really is a problem in quantum mechanics. And again, yet another reason why we don't really understand why deep learning works. Yeah.
Might not be the exact same thing you're thinking about, but so how are these symmetries exploited to make, or do we use smaller circuits, less qubits? Does the symmetries come into play?
I think the most generic way I can answer it, other than saying go read the paper, is that you have to enforce that your gates also restrict to that symmetry. If you have a symmetry group that's a bunch of Hamiltonians, you want to make sure that the gates commute with those Hamiltonians. But I would really read these papers. They're actually well written. And yeah, sorry. Yeah, go ahead.
So I think recently you and Seth Lloyd and others put out a paper about the symmetries are too strong.
Yeah.
You can also classically simulate this.
Yeah.
Can you say a bit about what kind of symmetries are too strong, or what kind of symmetries one would try to look for if you only want quantum advantage and no classical?
Yeah. So one thing you can say, so if your symmetry is too powerful, then your state space often goes from 2 to the n to something really small. So a simple example is that let's forget for a second quantum states. Let's look at Boolean functions. You have functions from 0, 1 to the n to 0, 1. So functions that are just taking bit strings of length n to 1. If you say that the function has to be permutation symmetric, for example, this is a state space of size 2 to the n, but permutations, there's n factorial of them, which is bigger than 2 to the n. But what it's saying, if you say it has to be permutation symmetric, is that all I care about is the number of ones and zeros. Because the order that they come in doesn't matter. So there's n plus 1 possibilities. And if I want to learn anything, I just query those n plus 1 possibilities, and I've learned the function. You have a similar statement in quantum. Instead of becoming n plus 1, it's like n cubed if you have a permutation symmetry. But if you want to learn it classically, you just kind of have to learn those n cubed degree freedoms, and you can do it oftentimes in the same way. So symmetries can be a blessing and a curse. Yeah. I don't know if that helps, but yeah. Yeah.
In the 2 design math that you have done, all of them are tensors, right? So you can take the first element of the tensor together and the second separate. You can separate out the whole tensor as 2 terms, and then it will be back to 1 design, right?
This? No. No, we have a squared here, right? So to take the squared, we have to do 2 of these. Like this formula here, I can't change to just 1. I mean, I could change it to say it's u this squared, but that's not the same as saying u itself, right? Like the square of a random variable is not equal to the random variable itself, right? Okay, so for the rest of the 40 or so minutes, I'm going to change directions. Oh, yeah.
That too, only for ground state, or is it?
Everything, yeah. There's I didn't put them up there, but it's been studied in virtually every setting, and there's an analog in every setting. VQE, learning, whatever you may want.
Why doesn't this appear in classical setting?
Because in classical settings, if you have a matrix of size n, it's a matrix of size n. It doesn't grow up exponentially in size. Whereas in quantum, when you add qubits, you're doubling the size each time you add a qubit. Actually, though, I will say, your question is valid, though, because there are a lot of situations classically where you do have similar things. But there are 2 differences. One is that, what I just mentioned. The second is that even if it does decay exponentially, you have polylogarithmic. So you can add bits. You can, to get computer precision within exponentially small, you just have to add more and more bits. We can't do that with quantum because we have to sample outputs. It's not like we can just add bits and get double the precision. If we want to get double the precision, we have to make double the measurements.
I see the sampling.
It kills you, yeah. And that'll be in the exercises, yeah. Okay, we're going to look at a different topic that's related now. So I want you to kind of put this all aside for now. If there's more questions, you can come ask me after. But we're going to look at a different idea here called quantum kernel methods. And there are relations to what we're doing here. But again, I just want you to kind of eliminate what we discussed here from your mind, and we'll look at a different model. Okay. Quantum kernel methods. Okay. Right. So kernel methods are essentially saying we do all of our learning with a kernel function. And a kernel function, you can think of it as something that takes in x and x prime, and it returns like a similarity. And, you know, if you have a bunch of data that's in some training set, maybe you can classify something or get some sort of prediction by like looking how close it is at your data set. And the idea here is that like you kind of encode your algorithm in the similarity metric. And we'll come to this, but like what I kind of want to get in the back of your mind is that, you know, that's kind of a similarity metric, right? We have an inner product in quantum mechanics. Why don't we try to use this? So that's kind of intuition, but let's maybe materialize this as we go on. OK, so kernel methods are all basically linear models, which means that, and I'm going to just give some notation here. We have some phi, which is a feature map. And we have some input space. So x, our inputs are drawn from some calligraphic x, which is an input space. And this can be anything. It can be like a set of numbers. It can be an image. It can be a graph. It can be, I don't know, text, whatever it may be. But all we have to do is say we have a map that takes this input space into some Hilbert space. And if you haven't heard of the word Hilbert space before, just think of like the space of quantum states that comes with this inner product. So as long as we can take our input state, whatever it is, and map it into some quantum state, then we have a feature map. So what's an example? This is not a quantum example, but this is also a feature space. I could say maybe x is just a number, and I don't know, I'd pick random features, sine x, cosine x, x squared, x cubed plus x. Yeah, I don't know. I don't know why I would pick this, but like, this is a feature space. And we can do learning with this feature space. Why not? Sounds reasonable, right? OK. So all the models we're going to look at take the form plus some b. So they're all linear, which means they take the form of some w times our feature space plus b. And these two, our w and our b, is what we want to find. So learning basically consists of finding the optimal W and B. OK. Now I kind of mentioned here that we really only want to use the kernel function. Like W here is like some vector in the Hilbert space or in the space. We don't want to have to ever construct this. Like this is kind of saying we have to like find some quantum state, whatever. Our goal is like we want to write everything in terms of this. So how do we do this? There is a very important theorem in kernel methods called the representer theorem. I am just going to write it informally here because the informal version of it is really all we care about. But you want to find proofs. The proofs aren't so bad, and you can like Google this, and there's tons of stuff on it. Even the Wikipedia article is good. But the informal way of saying it is that given a data set, and I'll just do our pairs again, xi, yi, I equals 1 to n. Given some data set like this, for many loss functions, which take in two inputs. So, f, x, y, we've seen this before. For many loss functions, the optimal w, which I'll say the optimal one, we often put a star here. So the optimal w star is in the span of the data, alpha I times phi I xi, sorry. Okay, so take a step back. What is this saying? It's saying that no matter how big the feature space is, it even could be infinite dimensional, something that we would never be able to access. It's saying that no matter what we do, our optimum is always going to be the span of the data. It's always going to be some set of coefficients alpha I times our features in our data set. So this is taking some potentially infinite dimensional problem and saying all we got to do is find the alpha I.
Is the intuition behind this that imagine that a space and moving perpendicular doesn't buy me anything?
Exactly, that's the proof, yeah, you got the proof, yeah. If you look online, you'll see the proof. It just requires setting up some formality. Anyway, but that's basically the proof, yeah. It's saying if you go outside of this, you're not going to gain anything because they're all linear models. Why would you go outside your support? That's the proof, yeah. So let's plug this in to here. And what we find is that, well, we get sum equals I equals 1 to n, alpha I, phi I, x I, sorry. This is really bad. Phi of xi times phi of x. Right? This is just our inner product. In quantum cases, this is saying that our whole algorithm is just calculating n kernels and then doing some weighted sum of them. Oh, and then the b, well, the b is just a constant. You can figure that out through learning. Yeah. Sorry, I didn't add that. But yeah, this is another number you got to figure out, yeah.
How does the f of x relate to the loss? What are we using the f of x for?
So, for example, one loss that this is true for, and this is true for many losses, but one loss you could say is L fxy, which is equal to the mean squared error. So this is a loss we could use. We have classification, +1, -1, and then we want to get as close as possible to the y's, which are either +1, -1. And this is one of the losses that has a representative theorem. But it's true for very many losses. Good questions. This is kind of nice. It's saying all we have to do is be able to find some way to take our inputs and put them into a quantum state. And then we do the rest from an inner product, which we can calculate on a quantum computer. Actually, that's another exercise, which will be how to calculate the inner product, but it's doable. It's not too hard to do. And that'll be in the exercises later, but it's kind of nice. And what I want you to think is these are feature spaces, and quantum computers give us access to stuff we definitely can't compute classically. We can put a state space, which is some really complicated unitary that there's no way we'll be able to do it classically, and maybe we can then use this to perform learning. There's a few good papers I would recommend if you want to just see the basic ideas behind this and different ways of doing this. Again, I'm just going to put archive numbers, 1804.11326, 2001.03622, and then 2011.01938. This idea is really elegant, and people have kind of taken different views of it. And if you want to see more of this, you can look at those papers. Okay. So high level, and actually one thing I'm going to come to, if Yeah, there'll be time. One thing that I'll come to is you can actually have provable exponential speedups in this setting. And we'll give an example later. Something, yeah.
Could you give us an example of like classical kernel methods? Like all of your examples, like imaginary and so on, right? Like.
Yeah, so like, this is an example of a kernel. Distance.
No, I want an example of where people actually use kernel methods.
Oh, I see, like in reality.
Yeah.
Okay, this was all the hype actually in like the 2000s. Everything from like image analysis to text used kernel methods in the 2000s. If you've heard of support vector machine, for example, that's one way of doing this. And one of the reasons why people love it is because it's linear. It's really easy to do proofs and like understand it. And it's kind of lost its like rage ever since the deep learning phase. But
these methods don't work as well as those.
They work pretty well. They actually, I think even now, if you don't have much data, like if you have like, I don't know, less than 10,000 data points, these actually kind of beat neural networks still. But one big issue with this is that, we'll come to this, but like you kind of have a scaling that depends on n. And to perform classification every time you need to do n kernel entry calculations, and this can be expensive. The complexity grows quadratically with n, which neural networks, it grows like linearly, so you kind of have issues when you have big data sets. Okay, so advantages of this idea. So we only need an inner product, which is great. We can do that with quantum computing. Linear models means we can do theory. It's really hard to do theory in deep neural networks and variational algorithm and stuff, but this is actually, like, there's a lot of really good theory here. And it's easy because it's linear. And one more thing, the optimum, often in closed form, or easy to find. What do I mean by this? Like, we use gradient descent in deep learning because we don't really have a better way of finding the optimum, but like these are structured problems that like the optimum is also often just an equation or like something we can find using like a package that's has some structure. Like it's convex, you know, like, so there's all this nice stuff that comes out of it. What's an example of this? Well, if our loss function is the following, our favorite mean squared error loss, then the optimum is just an equation. It's equal to, so this is our loss. And our optimum is just the following. It's equal to some row vector, which is the inner product with all the n data points. So we're trying to find, like our function as a function of x is just take the inner product with our n data points, times some inverse of some kernel matrix, which I'll come to. And then we put our our labels here. And this is just the kernel matrix of the data, which is an n by n matrix. So it's equal to x1, x1, x2, x1, all the way to xn, x1, and then x1, x2, and so on and so forth. So it's an n by n matrix. That's called our kernel matrix. And well, this is like a linear algebra formula, but it's in closed form. That's our optimum. It's kind of nice. How many people have seen this, actually? I'm just curious. Oh, OK. Quite a few people. Oh, nice. OK.
But is it still n by n in the quantum case? Wouldn't it be 2 n by 2?
No, this is just inner product, right? It's just saying n by the number of data. Right? The inner product is just something you compute. That's why it's so beautiful. Like, it doesn't have anything really to do, I mean, abstractly it relates to 2 to the n, but like as long as you can calculate the inner product, that's all you care about. And we can do that, right? When we have a quantum computer, we can do that. Okay, so I have like 15 minutes or so. I'm going to give you an example of how people use this to show a provable speed up, provably exponential speed up over classical algorithms. Yeah. Yeah, so you have to calculate this row vector with any new x. It's n calculations. But this guy is the same. You calculate this once, and you're good to go. That's the nature of kernel methods. It's kind of saying, like, I don't want one function, but I just want to have a function that I can calculate by comparing it to my data set. And this is the comparison to the data set.
Where's the quadratic? The quadratic is just in the kernel, the k?
This matrix is n by n.
So it's quadratic to train, I guess?
Yeah, it has quadratic complexity in the number of kernel to calculate, and also at least quadratic in like the calculate the matrix inverse and stuff. But like it's kind of like quadratic is the minimum. I mean, it's probably more than that in general. But like, if you have a big data set of like 10 million images, you want to avoid that. And that's why deep learning doesn't use this. Or part of the reason, I shouldn't say, yeah. But if you have a small data set, which again, we probably have in quantum computing, then like this might be a okay idea.
But if it's a small data set, then like, why are we even doing asymptotic analysis? Isn't the point of asymptotic analysis that n should be like, could be in principle be big?
Yeah, but sometimes like if your runtime is like exponential in n versus n cubed, then like that's fine, or n squared. Like, so I'll give an example of a rigorous speed up here that you can use with this. Like, I will say there's also people who have done work on like trying to get around the quadratics. There's like approximations that make it linear and stuff. But that's a good point. Like, yeah, if we care about asymptotics, then like, yeah, I mean, a lot of this stuff falls apart, yeah. Okay, so how did they prove the asymptotic speed up? This is an analog to Shor's algorithm, a learning analog. So they take Shor's algorithm and make a learning problem out of it. And this paper I'm going to go over is 2010 point. Okay. So what is the learning problem that they prove you can do with a quantum computer and not with a classical computer? The learning problem is basically a discrete logarithm, which is the basis of Shor's algorithm. So you have a prime number, p. Think a very large number, exponentially large in n. You have some g, which is a generator, and I'll come to this, of the integers mod p. So we denote that p, which is equal to 1, 2, all the way up to p minus 1. And basically what it means to be a generator is if we like have a number g, it's just a number, saying if we add g enough times, then we would get every element of this set. And all throughout this, you should think of numbers mod p. So when I say g, it's an exponentially large number, but I can add it by itself. And when I take mod p, it eventually recovers every number in here. So like, I don't know, if this is 1, 2, 3, like 2 is a generator, right? Yeah.
It's prime, right? So as long as it's not a power of p, it's a generator.
Yeah. And then s, random number in ZP, and you'll see where it comes in, but just you take some random number in here. What's our goal? We want to learn function. So if we want to learn the following function, f, which is a function of our number s. It takes in some number x in ZP, and it outputs one of the two possible things. It outputs +1 or -1. Outputs +1 if log gx is in s plus p minus 3 over 2. and -1 otherwise. And if you don't know what this is, don't worry. This is the discrete logarithm, which just means that log gx is equal to a, which implies that g, it's equivalent to saying g to the a is equal to x mod p. This is the thing that Shor's algorithm solves.
It's like PR over 2S plus.
P minus 3 over 2. Yeah, it's kind of taking half of this interval. Yeah. So, you know, the criticism of this paper is like, you're kind of not doing anything new. You're just taking Shor's and making it a learning problem. But hey, at least it's provable. And why is this hard classically? Well, I won't cover this today, but like you can kind of see why if you learn this, you can also solve the discrete logarithm. And we believe classical computers can't do that. So like, they shouldn't be able to solve this. To solve this, use a kernel method, which means I have to tell you what kernel they use, what feature space they use. Does anybody want to venture a guess at what you're going to use? This is a really hard question, but I'm just curious what people would guess. Close, yeah, that's kind of the idea. Well, the feature space, let me just write it, is a map which takes this into 1 over square root of 2 to the k. And k is a number that's chosen based off how many data points you have and stuff. But just think about it like some number roughly on the same order as like p divided by the number of data points, something like that. And then sum I equals 0 to 2 to the k minus 1 x dot g to the I. So it's saying, and I'll give a picture of this, which I think will make it clearer, but it's saying take your point x and then put in a superposition of all the points in this like discrete log space that are ith neighbors up to 2 to the k. If this doesn't make sense, I will give a picture that I think will clarify this, but that's the feature space. And notice this is our whole algorithm essentially. We've just said like, here is your feature space, and then just plug it into whatever kernel method you like. You could do kernel regression, for example. But all of our work was in like finding the right similarity metric. And there it is. Okay. Another criticism of this is like, it's kind of a useless problem. Like, when do you ever care about doing this in real life? I don't know, but like it kind of shows that at least you can do something with quantum that's provably powerful. Okay, so let's kind of like visualize this. Let's visualize this. So like you can represent the numbers mod p as like a circle, because you know you kind of circle back as you go around this. And like if I were to put like, let's say I put circles as +1 and crosses as -1 as our classifications, then like on this circle, you know, it kind of looks really random. Because like every time you do this, like you really don't know what's going to happen, right? But if we look at discrete log space, then our S becomes what's called a separate plane. So it basically says everything to the right of S is +1. And everything to the left is just a bunch of -1s. So what's our kernel then? Our kernel is basically saying, let's say like this point is x here, let's say that's our data point, and this kernel is saying take the equal superposition of all points within a neighborhood of that point. And when we take the overlap, we're going to get however many points are within the overlap of the training set and this area. So if you kind of think about it, like, it's obvious why this learns, because like all you have to do is find out, get enough points in your training set so you cover this space well enough so that these overlaps cover your data space. And, oh, sorry. And the reason we can construct this kernel is because we can do the discrete logarithm, which is essentially forming the state. OK, I'm going to pause here, see if there's questions before I jump on. But does that make sense, sort of? I haven't gone through the details because I think the intuition suffices. And the details are kind of just a bunch of math that I don't think is important now. But does that make sense? Yeah.
So, I mean, to restate, you're trying to learn a function which is like one side of this plane.
Yeah.
Which is what f is, why f covers half the elements.
Yeah.
And then you're saying, well, with this x, this feature map, you're taking a region of the points in this log space.
Yeah.
And so now when you have training data, you're like uncovering a region of that circle.
Yeah, because like, you know, your training data is going to be like random points in this circle. And you kind of want to see based on which points the circle is, like what the actual function is. And if you use a similarity metric that sort of finds which training data are within your region, then you can predict it right. Yeah.
What is the runtime of this in the number of samples?
Classically or quantum? So to form this state, you're saying?
Yeah, I want to compare with classic again.
I don't know if I can do it off the top of my head. I forget what the runtime of Shor's algorithm is. I mean, you basically run Shor's algorithm, and then you get that state. And then you have to do this for every training point.
But, I mean, it seems like in Shor you only really had like one n, which was like the size of
Yeah, you have to do
P.
this n times.
But here
Yeah.
you have like also the size of the training data.
Yeah, so it's like quadratic in the training set times the runtime of Shor's, something like that.
And this would be quadratic in the set and exponential in the
What's this? Sorry.
of the classical one.
Yeah, the classical, like you can't, I mean, I don't know how you would do this classically. If you were to form this state classically, like even just finding this would take you forever. Yeah, like the whole point is you can't find this feature space classically. Like this is a truly quantum thing. Okay, I have a few minutes left. I'm just going to survey the field here, just like I did with variational algorithms. But there will be some exercises later that I think will help aid people's intuition and give some more ideas in this field. But so main challenge, let me just say challenges, or you can think of these also as open problems. Kernels, hard to find. So like all the challenge in this whole field is finding a good kernel, and it's not easy to find one. That's basically a challenge. And this is true kind of classically too. Similar trainability issues. So sorry, my handwriting is bad. But if you take like a random kernels, you're going to have the same issues we talked about in the variational algorithms. Because like, you know, if your kernel is equal to 0 times some random unitary u x prime, I don't know, dagger here maybe, 0, then like if this is close to random, then this overlap is going to be exponentially small, and like same issues start popping up. So we don't want that. And a couple papers which talk about this are the following. And so these two papers talk about it. One of these is actually by like classical machine learning people who are experts in kernel methods, and they they kind of put out a paper that was like, this is hard to do even though it's quantum still. So like gave some perspective, but so same sort of issues here, but again, clearly there's some promise. There's some proofs you can do. And if you want to find a nice algorithm, all you really have to do in this setting is find a good kernel. And sometimes that's easier than training a whole algorithm from scratch. Yeah, that's all from me. Thank you guys so much. I'm here to answer questions.